video. I hope you guys are doing well. Is this everybody's last class before the break?
Yeah.
Nobody has classes tomorrow? Yay, I don't either. So this is kind of it for me as well. Well, thank you for taking the time to come down here and spend one last day with me until we take our break. And then, yeah, so next week, sorry, I forgot to bring my Kleenex box. I know you're all gonna be in tears to find out that we don't have class. You don't have to listen to me for 4 hours next week. But you can always turn on my YouTube channel. You can hear my voice anytime you want. But yeah, so we've got a nice week off coming. I'm gonna be leaving town on Saturday morning. I think I'll be gone until pretty much till we come back on Tuesday of the week after, which I think is April 8th. So I'll still be reachable. You can email me if anything comes up during the break or you're working on stuff, trying to get a leg up on anything. Feel free to do that. It's certainly no bother. I always like people to know it's never a bother to have questions or to want to talk to me about this stuff because I love this stuff. It's what I really enjoy doing. But I will be out of state, so be a little bit hard to do anything in person until we come back. I am going to have my office hours tonight. And I also will have some hours tomorrow, and that's because there is a homework assignment due tomorrow night at midnight. If you've started working on it and you have any questions for me already, during our break today, feel free. I've made a space for you to add some problems on my sideboard over here from section 6.3. That's what the homework is about. That's due tomorrow night. And it's about the kernel and range of a linear transformation. So that's really the only thing left to do before the spring break. There will be an assignment for you to work on for the Tuesday when we come back from the break. That's the very next assignment. It's already posted and it covers section 6.4, which we've pretty much already finished. And then 7.1, we're going to start chapter 7 today, actually. So we'll be able to work on that a little bit over the break as well. But we're kind of just back into our regular pattern now. We've got that second exam behind us and just have to get a few more weeks under our belt and we're gonna have this thing done. So not too far to go. Does anybody have any questions about any of that? So far, so good. Okay, so again, during the break, if you have questions on the homework for tomorrow night, throw them up on that sideboard for me because I should have some time to take some questions if there are any. What I've got on the board, as usual, you're used to seeing this from me, is the recap of where we left off on Tuesday. And we were talking about linear transformations. We're still in chapter 6. And we're looking at the two subspaces that we really want to get to understand a bit better. The kernel of T and the range of T. The kernel of T, remember, just to remind you here, the kernel of T, this one is a subspace of V. It's always a subspace of V. We wrote that down on Tuesday. And then the range of T, well, that one is always a subspace of W. Okay, so we have one subspace on each side of the linear transformation. And on Tuesday, we did some examples of calculating kernels and ranges. Since they are subspaces, of course, they have a basis and they have a dimension. And actually, that reminds me, there's something I did not write on my recap that I really should have. Does anybody notice, anybody who was here on Tuesday notice any really important thing that I forgot to write down on the board here? Which one?
Let's see.
You're thinking of the theorem. I know you know it. I know you know what we're talking about. Does anybody know the name of that theorem? The general rank nullity theorem. That's what you're thinking of, I think. Yes, exactly. Let's just put that in here too, guys, because there's never such a thing as too many times of writing it down. The general rank nullity theorem. And what this said and what we figured out on Tuesday is that if we take the dimension of the kernel of T and we add that to the dimension of the range of T. So if we add the dimensions of these two subspaces, it's always equal to the dimension of V. Sorry, it's a little bit squeezed in there, but that's just the dimension of V. And the nice thing about this is that usually we know what the dimension of V is. And so we can use that to help us relate the kernel and the range, their sizes to each other. Right? If the kernel is big, probably means the range is small. If the kernel is small, it probably means that the range is big. These two numbers, they kind of play in opposite directions, right? Because they have to add up to some fixed value, whatever that dimension of V is. Okay, yeah, so that's a really, really important result. And it's just a generalization of the rank nullity theorem that we had learned a couple of chapters ago. Right, okay, so we've got these two subspaces here, and then we introduced these concepts of one-to-one and onto and isomorphisms. So 3 definitions here to kind of remind you about. The one-to-one transformations, those are the ones where the kernel is just 0. In other words, the only vector in V that gets transformed to 0 is 0 itself. So that's the kernel being basically as small as it can be. This is basically saying the kernel would be 0-dimensional. In the case of a one-to-one transformation, the kernel would be 0-dimensional. Exactly. The opposite concept is the idea of onto. And a transformation is onto if its range is huge. The whole big size of whatever W is. So if the range is the entire, remember the range is just all of the outputs of the transformation. It's all of the outputs of the transformation. And if that happens to be all of the universe of W, then T is onto. Okay, so we have one-to-one, we have onto, and they're kind of opposites in some sense. But a transformation could actually be both. It could have a kernel that is equal to 0 and a range that is equal to W. And if that happens, we're going to say that T is an isomorphism. It's a pretty sophisticated math word. And it just means that T is both one-to-one and onto. And if that's the case, in this case, the 2 vector spaces that are involved in that isomorphism, they are isomorphic to each other, which I kind of talked about this on Tuesday. It really means that they are algebraically the same. I don't want to say literally that they're equal to each other because they're not the same looking objects, but algebraically, the way that things work in 2 isomorphic vector spaces is pretty much the same. If we have 2 vector spaces that are isomorphic and one person is doing calculations in one of them and someone else is doing calculations in the other of them, they can use that isomorphism to talk to each other, right? To understand each other's work between those 2 vector spaces. So that's a really, really powerful idea, okay? And I'm going to do another example of that here today as well. So you're going to get questions now, right? You're going to get questions. I hand you a transformation and I ask you, is it one-to-one? Is it onto? Is it both? Or is it neither? And to help us with that sort of 4-part multiple choice question, I have these bullet point facts over here that I probably should make another handout for this because this is super important, right? You're going to use this little 3-part bullet point list a lot. So if V is bigger than W, then without even looking at what T is, without even looking into the details of what the formula is for T, if V is bigger than W, then there's no way that T could be one-to-one. Just can't be. Okay, it might be onto. It might be onto, but there's no way that it could be one-to-one. We would have to check whether it's onto by looking at the range and seeing if it equals to W. Basically, right? The opposite scenario is if V is smaller than W, and in that case, there is no way that T could be onto. Without even looking at what the formula is, I can just tell you without even opening my eyes, T will not be onto. Right? It will not be onto. It might be one-to-one. And for that, we would have to figure out whether the kernel was 0 or not. Okay? And then the last situation is if the vector spaces have the same dimension, the same size, so to speak, then I can guarantee you that T is either both or neither, right? So you could just check if it's 1-to-1, then it would also have to be onto. If it's not 1-to-1, then it couldn't be onto. Right, so you could figure out yes or no on that. Again, you'll have to do a little bit of work to figure that out. Okay. But so out of the 4 parts, this is a sort of a 4-part multiple choice question. Is T 1-to-1 onto both or neither? You can always cross off 2 of the wrong answers before you even think about what T is. Just by looking at V and W. Just looking at the vector spaces that you're given, you'll be able to immediately rule 2 of the answers out. And that's nice to be able to do that. Okay. Yeah, so are there any questions so far on what I've said? I'm just summarizing again from what we did on Tuesday. We did a lot of stuff last time. I just want to see if everybody's feeling okay with this. Don't forget, I think by the end of class on Tuesday, we had 7 examples. And we made a table for all of them. We wrote down what's the dimension of the kernel, what's the dimension of the range, and is that transformation 1-to-1 onto both or neither. So we have a lot of examples in our notes now from various vector spaces. We had some polynomial examples, we had some matrices, we had some traditional vectors. So I tried to mix it up and give you a variety of things to look at. And again, this is the kind of stuff that's going to be in 6.3 and 6.4 in the homework as well. So kind of what you'll get a chance to practice on. Okay, well, speaking of practice, if everybody's sort of okay with the recap, and I know it's kind of a low energy day, I imagine, with everybody's trying to think about spring break. So I'll do my best to not make this too heavy. But with that as a background, let's just practice a couple of quick warm-up problems, all right? Let's see if we can do this. Here's the first one. I'd like to take an example of a linear transformation and try to ask you whether it's 1-to-1 onto both or neither. So we've got a good example right here that we can hopefully play with, okay? So my transformation goes from P2 of R over to M2 of R. So I'm going to plug in a quadratic polynomial and I'm going to spit out a 2x2 matrix. This is the way this is going to set up. And can anybody tell me anything helpful about the question we're trying to answer right away? Let's look at the dimensions of V and W. What is the dimension of P2 of R? 3, and the dimension of M2 of R? 4. So V is smaller than W, right? So then T cannot be onto, no chance. Okay, so let's write that down. I'll put a little bit of this into the writing here. So we know that the dimension of V is less than the dimension of W, right? Because we have 3 here, we have 4 here. So the dimensions are 3 and 4. And so therefore, this means that T cannot be onto. And if it cannot be onto, then I can cross off onto. And of course, that means I also can cross off both. Okay. So the only real question is whether T is 1-to-1 or not. And to decide that, I have to look at the kernel of T. So now we actually have to do a little bit of work. I have to think about the kernel of T. So let's just remember we practiced this a lot last time, but I just want to practice it again here. To figure out the kernel of T, how's that work again? I set T of V equal to 0. That's for the kernel, right? So I'm going to take T of V. I'm going to take T of AX squared plus BX plus C. And I'm going to set that equal to the 0 vector. Now, in this context, the output vector would look like a 2x2 matrix of zeros. Okay? And then if I just substitute what T of AX squared plus BX plus C is, I made up this kind of weird example. So the upper left corner is A plus B plus C. Upper right corner is 4A plus 2B plus C. Lower left corner is 9A plus 3B plus C. And the lower right corner is 16A plus 4B plus C. And that should be equal, still equal to all zeros here. And what you can see is that this actually gives me 4 equations, right? it gives me 4 equations. So what I would know from the upper left corner, a plus b plus c is equal to 0. And then from the upper right corner, 4a plus 2b plus c would be equal to 0. And then the lower left corner, same thing, 9a plus 3b plus c still equals to 0. And then the last one is going to be 16a plus 4b plus c, and that's still equal to 0. Okay, so they're all equal to 0, and so therefore I can put this into a matrix now. I can make a matrix out of this, 1, 1, 1, augmented with 0, right? That's the first row. And then the second row is 4, 2, and 1, augmented with 0. The third row would be 9, 3, and 1, augmented with 0. And the fourth row is 16, 4, and 1, augmented with 0. And my unknowns associated with these 3 columns are A, B, and C. Okay, so what I'm going to want to do is try to figure out whether the kernel has to be 0 here, or whether there's any other solutions. Okay.
Cool.
Now, this is not a square matrix, so you can't take a determinant or do anything like that. But we can do EROs, of course, right? So I already have a pivot here, and I'm going to use that to help me get zeros below that leading 1. Looks like this screen's on, doesn't it? Oh, I think so. Does it look like it's on?
Yeah.
It's on. I'm trying to turn it off now. Hopefully it will go off. Okay, it's weird, it's not very bright, but anyway, I can definitely tell it's still on. It should hopefully fade off at some point, it'll turn on. Yeah, so let me do some EROs here. Maybe I'll skip a little of the steps of this, right? So I'm gonna do some EROs without really showing all my work, if that's okay. I'll just jump to sort of a row echelon form. The first row, as you can see, isn't going to change. So I'll go ahead and finalize my first row with the pivot there in the upper left corner. In the second row, we will end up getting a 0, a 1, a 3/2, and then augmented with 0. And then the third row turns out to be 0, 0, 1, and 0. And then the last row actually turns into all zeros. So if I circle my pivots, which we always should do, they would look kind of like that. And as you can see, I do not have any unpivoted columns, right? I do not have any free variables. So if I was going to now solve this by back substitution, remember my unknowns here, A, B, and C. If I was going to solve this by back substitution, starting from the bottom, C equals 0, plugging that into the previous line, B equals 0, and plugging that into the previous line, we can find that A is equal to 0. They're all equal to 0 here. They're all equal to 0. And this just means that the kernel of T is just 0. It is just 0 in this case. And that is the definition of 1-to-1. Okay, so T is 1-to-1. Okay, so thus T is 1-to-1. Okay. That make a little bit of sense? So it's 1-to-1, but it's not onto. All right. Yeah, we could actually figure out it from this point, if we know that the kernel of T is 0-dimensional, and we know that the dimension of V is 3, then we actually know exactly how big the range is. The range is 3-dimensional, which is not big enough to cover W. W is actually 4-dimensional here. So the range is pretty big, but it's not big enough to make the function onto. Okay, questions? Well, let's try one more. Another warm-up problem of somewhat of a different nature here. I'll call this number 2. One more warm-up problem. I would like to show I'm gonna try to show that R3 is isomorphic to the set of 3x3 skew symmetric matrices. It's been a little while. Maybe been a little while since we worked with skew symmetric matrices. I'll remind you in a minute about those. The skew symmetric matrices, those are the ones where when you transpose the matrix, do you remember what it's supposed to be equal to? Negative of A, right? So a symmetric matrix, it would be equal to A, but for skew symmetric, it equals to negative A. And does anybody remember, by the way, what the form of a, because we're gonna need this actually, does anybody remember what the form of a 3x3 skew symmetric matrix would look like? Do you remember how these matrices have to be sort of laid out? Okay, zero, very good, Elihu. It's zeros down the main diagonal. Right, and then, can somebody help me, what about the other entries?
Negatives on top and others on the bottom.
Okay, the two sides of this main diagonal are mirror images of each other, but with minus signs on one side. I usually put the minus signs below the diagonal, so I'm gonna do A, B, and C here. And then I'm gonna do negative A, negative B, and negative C down here. That's the form of a 3x3 skew symmetric matrix. And what I'm claiming right now, what I am claiming right now, guys, is that structurally speaking, right, in terms of algebraic structure, this vector space over here, which looks like some weird thing, is actually quote unquote the same as just good old R3. So if you're kind of comfortable working with R3, then you actually should be comfortable working with the 3x3 skew symmetric matrices too, because there's a perfect correspondence between them. There's an isomorphism between them. And that's actually what we're being asked to do here. Let's be clear what this question is asking. It says, show that R3 is isomorphic to this other universe. To show that isomorphism, right, with this isomorphism notation, we have to construct T. So like on this problem, T was given to us. They gave us T and then we did a bunch of stuff with it. Over here, we don't have a T. But the whole point of this question is actually for us to make T. We're going to try to write down what T is. So let's see if we can do it. Let's see if we can do it. Okay, so for the solution, I'm going to define T going from R3 over to this other vector space, which I don't have a good notation for. So I'm just gonna say 3x3, the set of 3x3 skew symmetric matrices. Okay, so my inputs are gonna come from R3, my outputs are gonna come from the 3x3 skew symmetric matrices. And the formula that I'm gonna write down for this is, let's see, I have to plug in 3 inputs because it's R3 and they look like slots. So I'll draw 3 slots here for A, B, and C. And my job is to spit out as an output a 3x3 skew symmetric matrix. Can somebody tell me what I'm going to spit out over here? Exactly what I wrote above, guys. It's almost a trick question, right? I actually already gave it to you, right? It's just literally this matrix right here. It's just going to be this matrix right here. So we're just recopying basically what we already wrote above. That's it. That is the isomorphism. And you can bet that T is going to respect addition. It's going to respect scalar multiplication. And so it is a linear transformation. And it is also very, very easy to see that, well, so let me back up. Let me back up for just a second. This is an example of a problem where we don't really know the dimension of W yet. How come? Well, because we've never worked with that vector space, right? I mean, I know the dimensions of M2 of R, P2 of R, R3. I know those dimensions, But in theory, I've never seen the 3x3 skew symmetric matrices as a standalone vector space before, so we might not know what its dimension is supposed to be. So I want to be careful about trying to use anything here. See, if you don't know what the dimensions of V or W are, you can't really get any mileage out of these bullet points, right? You need to know these bullet points before you can really use them to make conclusions about T. But I can tell you guys that it's pretty clear that this T is an isomorphism, right? If we check, let's just check. So the kernel of T. The kernel of T, like how do you, Edgar?
Is that when you stop yourself from writing the W as like M3 of R such that with a condition?
I could have written it that way, and then we would be recognizing that this is a subspace of M3 of R. But M3 of R is 9-dimensional, right? Which is much larger than this vector space we're looking at here. So yeah, we are looking, so Edgar's making a good point. This is really a 3-dimensional, well, we don't know that yet, but it's a subspace of M3 of R. It's not all 3x3 matrices, it's just those that look like that, right? The skew symmetric ones. So that forms a subspace, and the dimension of it, I guess, remains to be seen. I mean, actually, it's not that hard. If you guys wanted to find a basis for the 3x3 skew symmetric matrices, you would know how to do it, wouldn't you? Write down the form of a vector, I already did that. Bust out the variables. There's an A, a B, and a C. You bust all 3 of those out, you'll be left behind with 3 basis vectors. So it's 3-dimensional. Okay, so let's stop kidding ourselves that we don't know it. This is 3-dimensional, this is 3-dimensional, they're both the same. Okay, they are, which makes sense. If I'm asking you to show that 2 things are isomorphic, they better have the same dimension, right? Because if the dimensions don't agree, if the dimension of V and the dimension of W don't agree, then C cannot be something, right? So they've got to be the same dimension. Anyway, the kernel of T is easy enough, right? You just take T of A, B, C, and you set it equal to the all 0 vector. In this case, that would be a 3x3 matrix of zeros. And then when you write down T of ABC, of course, that's just this matrix here, right? 0AB, -A, 0C, and -B, -C, and 0. And so now that's getting set equal to the all 0 matrix. And if you just match up the slots, well, you immediately see that A equals B equals C equals 0. So all of the values are 0. So yeah, the kernel is 0. So let's just put that over here because I'm running out of room. The kernel of T is just the vector 0, 0, 0. And that's the definition of 1-to-1. So T is 1-to-1. That would be the conclusion. It's 1-to-1. And since it has the same dimension as W, it has to be both or neither, right? That bullet point says it has to be both or neither. If we do know that this is 3-dimensional, they're both 3-dimensional, then as soon as T is 1-to-1, then it's also onto, right? So let me just add that as well. Sorry, I'm kind of working backwards here for a second. Actually, not that long ago, we had a professor come in to interview for a job with us in the department. And we always have them, I was on the hiring committee, and we have them come do a teaching demo. And the first thing he did, he walks in and he starts writing way over here. The whole board is blank. He starts his lecture over here and he starts going to the left. Have you ever seen another professor do that?
No.
I haven't either. I was like a little bit taken off by it. So I was like, this is not starting well. That's what I was thinking. This guy's got a backwards, but actually he did a good job. He's just, I don't know, I should ask him sometime why he goes from right to left across the room. It's not the way I read a book, but anyway. For a moment, I'm gonna steal his technique and go right to left, because I ran out of room over there. Right, so T is 1-to-1. I'm just gonna say since the dimension of R3 is equal to 3, which is equal to the dimension of the 3x3 skew symmetric matrices. Right, so since those are both three-dimensional, then by our last bullet point over there, T is also onto. And so T is an isomorphism. It's 1-to-1 and onto, so T is an isomorphism. Yeah, that's the point. Now, just be careful though that we understand when I say T is onto, I mean that it is onto this W right here. Okay, it's not, I'm not saying it's onto all 3x3 matrices. The world of 3x3 matrices would have been 9-dimensional, and T is not going to be onto something 9-dimensional. But it'll be onto this collection of matrices that look like this form. Anything of this form, we put it into this vector space, T will be onto that. Right, that's the point. Make sense? I should point out that when, and this is just a little remark, and I have not mentioned this to you guys before, but it's worth mentioning now. When you have an isomorphism, you actually have a transformation that is considered to be invertible. So in the case, this is worth writing down. In the case when T is an isomorphism, we can find an inverse for T. An inverse. In other words, T is invertible. You know what I'm talking about when I speak about inverse in the sense of, I'm not talking about an inverse matrix here. I'm talking about an inverse function. Right, a linear transformation at its core, it is a function. You guys know lots of examples of inverse functions, right? The inverse of the exponential function is the logarithm function. The inverse of the sine of x function is the arc sine of x function, right? So if a function is sort of 1-to-1 and onto, it has an inverse. You can, and what does that inverse effectively do? It interchanges the inputs with the outputs. It essentially turns the arrows around and gives you a function that we would write this way, T inverse going from W back to V. So you're actually going in the reverse direction now. Oh, you see? So you're going in the reverse direction. So in this case, what would that look like for this problem that we just did? Right? So in our example, the T inverse, right, it would go from the 3x3 skew symmetric matrices, and it would go over to the R3. So the inputs become the outputs and the outputs become the inputs. You're swapping the roles of everything. And how does the formula work? The formula is exactly the same concept, which is you just take whatever the outputs were. So I'm going to give you the formula right here. You plug in a 3x3 skew symmetric matrix, and now you spit out a vector in R3, which would be ABC in this case. There's a perfect correspondence, in other words, right? So for every triple of numbers ABC, we can make a skew symmetric matrix. But we can also do it in reverse. We can start with a skew symmetric matrix and associate with it a triple of ABC. It works both ways. And so there's an inverse for this isomorphism. We can kind of reverse everything, right? The outputs become the inputs become the outputs, but the correspondence is the same. The correspondence is the same. And it works actually in both directions. In both directions. Isn't that cool? So it works in both directions. So we can talk about a T inverse. I think there's a homework problem. This will be for after spring break, but there's a problem where they ask you to find the inverse transformation for some linear transformation. And all I'm trying to say here, guys, is it's easy. All you have to do is take the original formula here, right? And just make these the inputs and these the outputs, which is just what I did right here. So you're just swapping the positions of the inputs and the outputs. That's all there is to that. Questions about that? So if you get bored with R3, you decide, I'm tired of, I took a whole 250A on that, I'm kind of done with that. You can turn everything into a 3x3 skew symmetric matrix and do all of your math work in that universe instead. And then hand me that paper and I'll be able to translate it back into R3 again. Because there's this perfect correspondence. So no information is lost by doing that. It's pretty neat. Okay, guys, I'd like to take a few minutes to let you practice. Whoopsie, I'll get that. It's okay. Oh, it's under your. I would like to give you guys a few minutes to wander around the room with your partners and try a few of these problems. So let me send some group works around. And I will, of course, as always, come around and give you guys a hand. 1, 2, 3, 4, 5, 6, 7. And I'll leave you guys out. There we go. Can I erase this? I'm going to erase it so you guys can come up. Come on up, Vinny.
Actually, right there.
Yeah.
Yeah.
Yes. What's the same thing? This is the same thing. So the zero vector is just zero. In this vector space. I'm gonna get this.
I don't really remember correctly down.
Go ahead.
He said when it's a zero vector, not to write it down. No. I might have missed.
The zero vector should never be put into a basis.
Got it.
Vector,
Okay,
that's a totally different
Okay,
thing.
got it.
Totally
Okay.
different.
Thank you.
Oh, I'm not leaving.
Guys, grab some board space here. I'm erasing for you.
Dude, I'm not on weekends. I'm just. So this week homework and then starting Monday. Every weekend. You know, if I'm not working, I'll be actually saying.
Come on down. You need to have 2 or 3 partners. Not work all alone. Anthony, that includes you, Karen. Find some partners, please.
I'm gonna use it. We're open. We'll be right back.
What's that?
My teammates left.
Oh, no. Well, these guys can help. Why don't you join up with those guys? Okay, do you want to use whiteboard? I think it would be better. That way I can like swim the distance, and if I see something wrong, I can come sailing in and save you. Glad to do that. All right, we're not making this guy do all the work, are we? You need to erase this. That, what is W vector? 2x2 symmetric, maybe 1 dimension.
We're going from 4.
Write down what a 2x2 symmetric matrix looks like. This is symmetry. It says 2x2 symmetry. What is the form of a 2x2 symmetric? You're A, B, symmetric B.
The dimension of 8.
That's symmetric means shape transfer equals negative. So that would mean that I have to basically, I have to have a mirror across this diagonal. D and the B, they have to match up. But the diagonal numbers can be anything. Oh, so what's the dimension? Oh, so you got 4 to 3 here, on your dimension. So you get tired, you gotta pass that marker right up. Make sure he's doing this. Secure the work. Okay, good. That's what I want. How you guys doing? Hey, I'm really glad you saw the division. Even though it's a 2x2 matrix, they have to be symmetric.
I know.
So that's why that should be part of W.
Oh, there's three on the.
Basically, for symmetric matrix, your matrix is gonna look like.
Okay. Was it find out the year?
So you've got the phone number, you've got 3 here, so we'll just start. You already know kind of the relationship.
Is this one over 16?
Might be on, but it cannot be 1-to-1. Keep going, I'll let you, so far it feels good. Getting. Oh. Did you check that that's the base?
Yeah.
Oh, I know what you did. You calculated T of 1000. What's going on here? Was looking at the range. Range T is the span of. And then you take the base of our weight, right? Yeah. 0. Yeah.
So the other one was.
So what you need to do is you need to calculate this, calculate this, calculate this. Or.
I only did like the year.
Your entire universe.
Yes, no, you're right.
Matrices, guys. Look out at more matrices and then figure out what a basis would be. I thought it was.
Wow, it was good, boy.
It's a little fast for me. Oh, okay, great. Have you guys doing okay?
Oh, you just minus it out.
So you got your spanning set for the ring, and it's only 3-dimensional. You know it's not 1-to-1. That's all good.
So it goes.
So the question is just whether it is onto.
I mean.
So onto would be that the range is. Now W is 3-dimensional. So the real question is, what is the dimension of the range? Is it all the 3? It looks like it. I've got 3 vectors here. You can check to make sure they're Li. Because it's possible that they could be LD. So that's what you gotta check.
So you wouldn't just do like the.
Well, if you guys.
Yeah, so what you're gonna wanna do. You wanna figure out what is T of X squared, and what is T of X, and what is T of C. So you can respect that.
So the reason I thought.
And then you can break it in terms of just these basic. What you need to do is use these givens. Now, these 3 givens are not the 3 givens that you have right here. So what you have to do is manipulate. And we'll have you talk about that. You need to manipulate this given information. Ready to start?
Yeah, all right.
Sure thing. Does anybody need help?
So it's gonna be T1 minus T X plus 1 minus T1.
Okay, I will tell you it's less than before. Because when we're talking about two agencies, normally that would be.
Yeah, I think like,
But because they're symmetric, that's.
like abstract.
I would recommend that you write this on something big that looks like fun. If you just figure
Are
out.
you doing it like down? Or
Let's figure out what it is. Great for finding.
Minus 0.
Here. Not necessarily.
Oh, is it, yeah, that's these.
Right?
No, you're right.
So if I transpose.
So the B is -3.
So the AJ on that diagonal. The B and the B have to.
Yeah.
And the 0. This could be a different. So based on that, what.
They're doing it
Right, I'm expecting this is. So
B is
Now
right.
you go to your list. You guys do okay?
No, we put T of 0.
0, 0, 1. I wrote this one across, I wrote this one down. -1, 0.
I just want to see y'all separate. That's not. Wow, this does not happen.
Yeah, yeah.
That's actually.
Great, so -3 minus 0 plus 1. EROs, how many are each of us? Midterm. Quantum mechanics. So like psi,
Absolutely.
The electronics.
Anybody need a hand?
Don't, don't. Or if you have to take physics, too, that will learn it.
Yeah.
So I think 57, I think I failed the class, but I kind of.
You get the next one.
Love
3 plus 3 is 6.
So the dimension of W. How do they know the dimension of W?
Oh, no. Oh, so you got these three. Yeah. And technically you started with 4, right?
That's hard.
Right. This one, this one, this one, you got rid of one.
Oh, because we already found. Okay, gotcha.
And the rest of
That's how I do
technically you would have to check.
Oh, no.
Somebody playing with you could say, oh, well, this one was actually.
Oh, you're right.
Oh, actually, you're right, these are L.
Yeah, I know you have to.
Face value, then these.
Oh, I see.
Were the. Reporters?
Anybody need a hand over here?
Yeah, we're good at it.
Working it all out.
Yeah.
Those numbers, those look very familiar. Look at this. You guys doing okay? It's all zeros, yeah. So you get rid of that. You get rid of that. So the dimension of your range should have been only 3. Like, see what they have over there? They have 4 matrices listed, but then they removed the collapses because it was all zeros. The other 3 matrices, technically those should also be checked to make sure that they are still Li. But they will be. And so the dimension of the range is 3, and W is dimension of 3. Because those match, that means the range of C is E to W.
Okay, that's actually good.
You did all the work, I'm just gonna put the pieces together. So you have to, when you're checking for onset, you're asking, is the range of C just as big as W? And that can be analyzed from the perspective of.
Yeah.
The dimension of W. What's the dimension? All right, very good. Why don't you try a second?
Well, don't you have to like divide this by 3 to get into?
Anybody need a hand?
I got it.
Okay, let's see. So that's gonna be cool. Like, wait, but it's no, it's. What is the call space? No, that's great. Okay, that's no,
Yeah.
The safety of the law.
okay.
What about this?
You have to be very.
Well, that's what, no.
I already took it.
I'll figure out. Good. You could say, you know what? I'm not worried about it.
It's just like straight 0 to like. So.
This, you know.
Like we read about.
No, that's right. So that you can grade.
Then it's gonna be.
The matrix 0.
Is that the original?
Oh, yeah.
Oh, is it like that way?
No. Oh, it's quite.
Like the.
Yeah, so let me. Oh, just leave it like that. There's it's a price tag. It's not a big. So, yeah, but the point is that you are moving.
No, you're good.
Calculating.
Okay, the T is 1 to 1 both are needed. Will mention
This
which
is
of this is two.
That's a basic. Now, on this. You already know it's not gonna be important. That's because some of these are gonna be LP. When the range calculus stuff is like, so if ones are like zero, about like. Yeah.
Well, that's what it is.
Negative one. So I can already spend $1,000. Then I'm down to over 3. You can check.
Yeah.
So when you do, you lay them into the ground.
Yeah.
That one. They're running, they're so absolutely. Oh, it's scary. We're so the point is that. These are all back there, but that's the way they're LI.
How do we get 2 dimensions if we only started, we only have 2 dimensions?
Is the back there.
Keep two bars.
That works. That works. Yes.
Yeah, what?
I am. You are, because it's asking you to understand how.
Well, it's because third equals that you have a dimension, because third equals range T is what they
Yep, you're doing.
Anybody need a hand? Check this with me. 3 and 3, it is onto, but it's not 1 to 1, it's all in. Very well, very well.
Okay, I know what you're
Oh.
No, thank you. So just have one thing. You're off to a very good start. And I think it's excited to.
Oh, yeah.
Okay, we write it down to like here. And then show me.
He respects that. We've already got this. And then I think they gave you this stuff. And so then you just figure out to that. Probably that. And then once you know what that is, because that one is all. Should be. Then what they use.
Then we all like.
It's not.
Here again, so we define.
Anybody need help?
Define X and then define X squared, so that then we can put it all together, so we get X squared plus X squared.
On number 2, right?
Yes.
Now then we have X squared.
So like these make.
Yep, and see it 1 E. Yeah, so you should go right down to. Yeah, that's the next step. Looks good. Looks good. Bust that thing apart. Bust that thing out now. It's coming along all right. Now on. But that was great. So that could be the answer for TM AX term plus BX plus C. I'm gonna recommend that to help you with the other parts, you should compress that into one single matrix. So give yourself an equal sign and make a bigger matrix where you have each slot has an expression of A, B, and C. But you're doing great. And actually, could you do me a favor? Somebody else take a turn. Just to kind of trade off for a moment. Thank you. Thank you. Thank you. Let's see, Fook and Antonio and Nathan. Zero, you got so so far it's 1-1. Now we're trying to figure out, you know, actually the point is I should point out, we already chose because of the three dimensions. So it is 1-1, but it's not, we can already do part D. We did part D before we did part C. But to do the range, yes, you can go ahead and I'll let you take it down there. You actually are all. It won't take you much. Yeah, go ahead. Good job, Anthony. Good. So how do I write? He says, how did you do it? You can use your paper and just write one big.
I mean, you can just read it. Above,
Where you sort of press the upper left slot is just gonna be minus 2B. Combine. Now it's. Don't basically have to do that for the first question, but you're gonna wanna do it for the later part of your part. Okay. Good job. All we can do is addition and scalar multiplication, and then first subtraction is kind of like.
Yeah. Yeah, it's like.
Okay, that's fine. Yeah, mine is just the effect.
Yeah.
It will still work, because you know what T of X plus one is. I'd rather go that way.
Yeah.
Good job, good job. Nice job, guys. That's looking fantastic.
I'm looking out for
Are you guys working on the kernel? The kernel is on that one, and he's going to what? I have a front sitting for you here.
I'm sitting at.
I couldn't figure out this kernel without having to write all of it. Without having to see because the entries in that matrix are nice and. But what Daniel's doing is fine. Like, that's totally good. Totally.
We do have some.
Okay, basis for the range. You got it. So
Where's my answer key? You said you could do zeros.
Oh, yeah. This is your basis. Let's find out. Oh my gosh. Perfect. Perfect. So you guys are done, right? Yeah. Do you understand everything here? Pretty good about it? All right. Fantastic. Fantastic. Good job. Good job. You can just take a break, and you don't even need to erase that. You can just leave this up. Good solution. Oh, yeah. Thanks. Good job. Anybody need help? Yeah. Yes. I did great, and when I- That's his great.
Oh.
It's just 2 by 2. So, why are you setting it all in? You can figure out how to. No, if you don't know writing how to fix this. Like,
Just
it's actually pretty easy and sort of.
That's the. Skip it last time because we worked it out over here. Let's just get over there. I guess that's right. See.
You're actually. So.
No, but.
Either way, it's fine.
So then just find out.
Total was 0, right? Everybody following this okay? All right, sweet, sweet, sweet.
Let's do arrows.
Nice, that is tremendous. By looking at it, you can see B is gonna be 0, and therefore the A is 0.
I like the first.
That's are all 0.
Yes.
By the way, I already.
Sign up P1.
Oh, you did that already. Great. So, part B says if it was 1, 1, 2, 3, either, well, it's 1 to 1, and it's not.
Yeah.
Nice, nice. Good job. Good job, good job, good job. Yeah, this would be a perfectly good answer for the first part. Absolutely.
That's
This would be fine. I just want to point out, that if you want to, this will actually help you with your parts. The rest, all is. Combining one sorter.
It's all. Well.
So, going for your basis.
For me. This
Oh, okay, nice. Yeah. There's a lot of them.
That is what it's. So great, you know, the additional would be. Oh, well, then if I have to go right now, then you know that, you know, we're good candidates. So.
Hey, guys, I'm just going to kind of semi cut you off here because I want to do a little bit more today, but I also want to give you a break. So if you get to a good stopping point and you want to take a break to go outside, wash your hands, use the restrooms, whatever, take a lap around the hallways, this would be a good time to do it. At about 4:15 or so, I'm gonna start back, I'm sorry, but more like 4:17, I'm gonna start back up again. So I'll see you guys back here in 10 minutes.
Professor.
Don't worry if you didn't quite finish. Something like that.
5:10.
Oh, 5:20. Sorry, it's not 4 o'clock. That clock is wrong. That's why I'm using that clock to tell you. Sorry, I'm gonna start again at 5:20. I misspoke. I was reading the clock on the wall, which is strong. 10 minutes from now. Did you get it? Technically, yeah, and you're gonna get rid of this one. Never in a basis. But then these three are going to be helpful. And so that means that this is going to be your basis for the ratings. You, unless you already know that it's how much you want to go. The kernel plus the dimension of the range. That's equal to the dimension of B. And in this case, what is B? B is R4, is it? No, B2 of R. B of R is 3. 0. Oh, so I already know the dimension of the range is 3. I actually know that without even having to do the EROs. Makes some sense? Okay, great. All right, sure, no worries.
Oh, yes. C minus.
I was looking at the.
Yeah. You guys feel pretty good about all that?
I think we got.
Is that last one, is it 1-to-1, onto both?
I think you said it one.
One.
Only.
Only one. Correct. That is the right answer. Good job.
So, yes.
Take another picture. Now,
Yeah.
he just fixed it for you. I'll make sure we have it right. Thank you. You're welcome. Oh, somebody else? Alright. I don't want to be too anxious. I'll erase it for you. Okay, then can you write 6.3 with a line under it? Guys, if you have any homework questions, you can write them on the sideboard over here. I'll try to save a little time. If not, don't worry about it. I'll also be around for office hours.
I started. Yeah. A couple.
Thank you, Andy.
Yeah. Probably. I think 6 or 9. Yes.
Yeah,
Oh, 6.3 number. Oh, I'm probably in the wrong section, that's why. Yes.
Like, I don't think I signed that one.
yeah, you just like.
It is on.
Okay, got it.
No, I was like. She's trying to. He's up to her chest. On his stomach. I know. Now. Yeah. Oh, no, I don't. That's a lot. Just in your favor.
Okay.
Yeah.
I do.
You know, that like, it's just-
Buy those like.
the rest is the same.
Yeah.
Yeah.
It's like the.
Okay, because you know
I
what?
think about it. Yeah.
That's making a difference.
Or yesterday.
I have one.
Yes.
Okay.
So we'll see on from the inside. And I feel like it's sweet, you know?
Yeah.
Ash or something like further carrying them into. Sits in on.
What?
She gets there.
What's that?
Yeah.
No, so, yeah, I know the cash for the permit.
She's up.
Like, in-
You know, Ashley sweets like a.
They have a clothing.
It's like a material.
Where they get this?
I think, yeah, like I, it's like, you know.
Or vehicles.
That's just a different- Oh.
It's
Yeah.
like,
It's very, it's a good, it's a very good.
Is it made in Kashmir or like, is it like just like a?
Cashmere is a very thin.
I know Kashmir is something
Like
like.
a monkey.
Yeah.
It's not a it's yeah. And then cashmere with K is something that's a. So we eat.
yeah, like.
Hear that often, that's why.
Yeah.
Right.
Yeah, the booster,
Kashmir? Oh, that's the.
Yeah,
I
especially
didn't
yeah,
know
you-
what it was. I've been wearing this shit for like past like every.
Sorry, you're sitting for-
Last week, I was like, what? I'm getting into the. I watched.
I need some new pants, but I might want to. Meet
Bro,
less.
don't buy it from here, bro. Buy it like. I-
Oh, okay,
I-
yeah.
That's
That's good.
Oh, Uniqlo.
Yeah, that's-
Yeah.
I did them.
$50 $50.
For my son, I think kind of like.
Bro, team, come on. $4. Bro,
But
team
for
was a
myself, I
risk,
did-
bro. Team was a risk.
He was out there all point for.
Or like fish chip. It's a crap. Dude, I bought a shit now for my
Okay.
like sibling on it. Dude, the inside of the shit now was all rusted. I threw that shit away. It was like $5 though. So I can.
All right, everybody, it's about 20 after, boy, time flies around here. I think this might not be a bad time to pick things back up. There might be a couple people still wandering around, but only got about a half hour left. Thank you so much for the good effort with that group work. I do have the solutions in Canvas. This is gonna be one of those things where, okay, we're gonna take a week off and then we're gonna have another several weeks before we have to think about this for an exam. So something like this group work will be good to go back to and look at again, right? So, but at least for today, I think most folks had a good chance to kind of think about those problems. And yeah, if you have questions about any of that as we continue along, by all means, feel free to ask me. I'm gonna spend about 20 minutes, just 20 minutes starting chapter 7 right now, so that when we come back from the break, we're not just like starting from scratch. And then I'll try to save about 10 minutes at the end to take a couple of questions off of the homework that you're working on for tomorrow night. But guys, you cannot, in good faith, have a linear algebra class if you don't talk about eigenvalues and eigenvectors. You cannot do it. It's one of the, okay, I mean, there's this one guy who thinks you could do linear algebra without determinants, but that's another story. But this is just as big of a deal as that. You're gonna see in a few minutes, determinants are gonna make an appearance here. So again, it begs the question of how do you do linear algebra without determinants? I don't know, but you also would never go through a linear algebra class without seeing this idea here. This is, by the way, the last chapter before we're going back to differential equations. And we're only gonna need a couple of classes on this, so it's gonna be not too long till we're gonna go back and do differential equations, which is always exciting for me to sort of see the whole class come full circle. We get back to the stuff that this was all motivated for us to learn this stuff so we can use it, apply it on the differential equations. So that's a reason to come back after spring break, everybody, right? We're actually gonna see why this stuff we've been toiling away at for the last 6 weeks is actually useful for the real world. But before we do that, we have this very, very important concept to go over here. So throughout this chapter 7, A is going to be an n by n matrix. Okay, so always a square matrix. And I'm gonna just jump straight into a definition right away. So normally, by the way, I'll be using mostly 2 by 2, 3 by 3 matrices. Maybe once in a while you'll see something a little larger, but usually n will be 2 or 3. And here's the definition. If V is a non-zero vector, so if V not equal to 0 is in Rn. So we have some vector in Rn, the n is the same n matching with the size of the matrix here. And lambda, this is a Greek letter, and it's very standard to use this particular Greek letter for this. Lambda is a scalar, so that means it's an element of just the real numbers, such that A times V, okay, quick sanity check here. Can I even take A times V? Well, A is n by n. V is a vector in Rn, which I'm going to be drawing as a column. That would be an n by 1 column, right? So let's just write this down. This is n by n. V is n by 1. So I can calculate that, and the result of this multiplication will be an n by 1 matrix. And if it happens to be equal to just lambda times V again, if this is the main equation here, A times V equals lambda times V. In that case, we call V an eigenvector of capital A. We call it an eigenvector of capital A with corresponding eigenvalue lambda. So the lambda is the corresponding eigenvalue, and we can make this into kind of like a pairing, and we can put the lambda and the V together, kind of associate them together. This is an eigenpair. for A. Okay, so we defined eigenvalues and eigenvectors together because the two concepts go together, right? You can't have eigenvalues without eigenvectors. You cannot have eigenvectors without eigenvalues. They are part and parcel of this same theory we're talking about right here. So they always come together as a package deal. Again, we only talk about this for square matrices, okay? And this equation, AV equals lambda V, is the most important equation in chapter 7. Well, let me say that again. This is incredibly important. It is the most important equation in chapter 7 because it's where this whole thing starts from. If we don't have this, then we don't know what in the world's going on, right? The reason I'm emphasizing that is that this equation will at times seem to be in the background. Like, we're not going to have this in front of our faces the whole time. It's sort of when we get into the mechanics of how we find eigenvalues and eigenvectors, for example, we're not going to necessarily need this equation to be directly in front of us, but this is the starting point of this whole theory. And so it's very important. Let me draw a picture here to kind of show you what's going on. Maybe I have a vector V that looks like that. And if it's true that A times V is equal to lambda times V, guys, lambda is just a number. And all you're doing is stretching the vector V by some scalar number here. So if you were to do that, what would happen is the vector would just get stretched out. And so the vector AV would just be a scalar multiple. It would be a stretched version of V itself. So in this picture, V is an eigenvector in this example, in this little visual that I'm drawing right now. Of course, if n is equal to 4 or 5 or 6, you're probably not going to draw pictures of it. The dimensions are too high, but at least in a two-dimensional case, I could visualize it this way. So I have a vector, I multiply it by A, and what happens to it? It only gets stretched. It does not turn. It does not change direction. Now, I should point out that the AV could be just a fraction of V. And that's because the lambda might be like, I don't know, 0.1 or 0.3 or something like that. It could be less than 1. So when I say that the vector is getting stretched, I should say it's getting stretched or it's getting shrunk down as well as another possibility. Or there's even another possibility, which is that the lambda could actually be a negative number, which would flip the vector pointing the opposite direction. So let's draw one more example. It could go down like this instead. So the AV could get flipped. So 180 degrees, basically, is what I'm saying, right? But you can see somehow it's all kind of lined up on a line that is determined by the vector V. So that's how an eigenvector looks. Now, if we had something like this, where the vector V was here, and then the vector AV was over here, now this would not count. In this case, the vector V has not been stretched, it's actually been turned. So in this picture, V is not an eigenvector for this example. Just trying to give you a visual appreciation of this. So in that case, we would say, no, it's not an eigenvector. But yeah, this is kind of the idea. Let me give you an example that actually where we have an actual matrix to work with here. And then, like I said, we're just kind of getting a little bit of a warm up into this. I'm not going to go too deep. Let's suppose that A is the matrix 4, 3, and then 1, 6. Just take this little 2x2 matrix, and I'm going to take a vector V, and I'm going to use the vector 1, 1. Okay. So here, if we take those two givens and I calculate A times V, so I'm just going to write down my matrix 4, 3, 1, 6, and I'm going to multiply it now by the column of 1 and 1. So if I just do this matrix multiplication, so we haven't been doing matrix multiplication too much lately, but hopefully we remember we're taking dot products of the rows of the matrix with the column vector that we were given. 4 plus 3, that would be 7, and 1 plus 6, that would be 7. And look at what has happened, right? The vector v, which was 1, 1, has now been stretched to be the vector 7, 7. In fact, this is just 7 times 1, 1. And so there you go. You have your eigenvalue, eigenvector equation. The lambda value here would be the 7. That's the stretch factor. It's just a number. And so AV is equal to lambda V. So this is showing it with, instead of just this is the picture, kind of visualizing what's going on. Now here's kind of how it crunches out with some numbers involved. Okay. And so we could write down, maybe just to wrap this up, I could say, well, we have 7 and 1, 1, and this is an eigenpair. We could think of that as being an eigenpair of A. Okay, so just an easy little example to get us started with here. We're going to learn after spring break, and especially when we go back to differential equations, why this is important to find eigenvalues and eigenvectors for a matrix, for a square matrix like this. It's like, what's the big deal? Who cares? Right? What's it matter if A times B is equal to lambda times B? Doesn't seem to have any relevance right now. It is going to be hugely important, especially when we go back to differential equations. So you're just going to have to come back after spring break and learn a little bit more about that. What I want to try and do right now, though, is just explain how do you actually find the eigenvalue, eigenvector pairs for a matrix. Okay, that's something I think I can handle in 10 minutes. So let me give a quick little chat about that. So how to find the eigenvalues. By the way, I sometimes abbreviate that E values. Eigenvalues would just be E values, and eigenvectors would just be E vectors of a matrix A, which is n by n. This is kind of a nice little piece of theory here. And I've got a little chain of statements to present to you to kind of explain this a little bit. It turns out that when you're looking for the eigenpairs of a matrix, you're generally going to start with the eigenvalues first. You're going to try to figure out what all the eigenvalues are, and then after that, you can hopefully go back and figure out the corresponding eigenvectors. So let's just write it out this way, guys. Give yourself a little bit of room here on your notes so you can have space to do this. So lambda is an eigenvalue of A, and I'm going to give you a chain of statements here. I'm going to give you a chain of statements here. This is going to be if and only if, well, to be an eigenvalue, there would have to be another eigenvector as well. So there exists a V not equal to 0 with AV equals lambda V. Okay. Now, what I'm going to do, I'm going to just do a bunch of statements here on the right-hand side. I'm actually going to sort of ditto this whole thing again, but I want to set it up where I have equals 0 on the right side. And in order to get 0 on the right side, I just need to subtract. I need to subtract this over to the left side. So the thing is, when I subtract it to the left side, do you agree I could factor a V out of it? I have A right there. That's AV. And then minus lambda V. Now I gotta be a little careful here. I can't just do this. Because if I write that down, I'm writing something that makes no sense. This is a matrix minus a number. I wouldn't know how to take this matrix A and just do minus 7. Right? That doesn't really make sense. So instead, what you have to do, we've seen this before. What we have to do is slip our good friend the identity matrix in there. Right? That identity matrix is like multiplying by 1. So it really has no effect on the calculation. But it now gives me something that's actually a matrix. So it wouldn't make sense to just subtract 7 from this matrix, but I could subtract 7, 0, 0, 7. And then that would be a reasonable thing to do. Okay. So all I've done so far, guys, with this little calculation is I've just moved everything to the left side. And notice what you have here, guys. You have a vector V that gets killed by the matrix A minus lambda I. When I multiply A minus lambda I onto V, it becomes 0. What does that tell you about where V actually lives? Let's see if we can tie this into some earlier material. If A times a vector becomes 0, what does that tell you about that vector? It doesn't have to be the 0 vector. In fact, we said here that it's not the 0 vector. But does this sound familiar? If I have this equation and I'm asking what are the vectors V that make this equation true, what am I looking at here? Say it again. The null space. We're talking, it's exactly right. That's exactly what I was looking for. The null space of the matrix. Guys, V is in the null space of A minus lambda I. That's exactly what I was hoping you'd say. Yeah, that's it. Yeah, it's a good guess. It's a good guess. And actually, this tells me because V is not 0, right? V is not 0. That tells me that my null space of A minus lambda I is not 0. It's not the 0 vector. There's at least one other vector. It's going to be my eigenvector, actually. There's one other vector that is in this null space. Does that tell us anything about the matrix itself? You think you know? Careful. Okay, we're gonna get to that. We're gonna get to that. The null space is not 0. Okay, very careful. If the null space is not 0, what does that tell you about your matrix? You were close, but you said one thing not quite. What did you say? Can you say it louder?
We can take the determinant.
Before that, what'd you say? You said it was invertible? Okay. Can somebody correct that? If the null space is not 0, then this matrix should be not invertible. Not invertible. If you go back to the lists, right? Sorry, I didn't mean to put you on the spot. It's my bad. A, B, C, D, E, F, G, H, I, J, K, L, M, N. There's big long lists of things about invertible matrices. If a matrix is invertible, its null space is 0. Okay? So if the null space is not 0, then the matrix is not invertible. Right? And if the matrix is not invertible, what can you tell me about its determinant? It equals 0. Exactly, it equals 0. This is the second most important equation in chapter 7, behind the one that's on the board on the left, in my humble opinion. So this is called the characteristic equation. This is called the characteristic equation for A. It's called the characteristic equation for A. And this is an equation that will allow you to solve for the lambdas. Once you know what the lambdas are, then you'll be able to make this matrix and calculate the null space, and that's where you'll get the V's from. So how do you find eigenvalues and eigenvectors of A? You solve this characteristic equation for lambda. And then for each of those lambdas, you can find the V's that are in the null spaces of those matrices. It's basically how it works. I should show you an example probably. That sound okay? Let me see if I can show you an example really quick, and then I'm only going to do a 2x2 example today, and then on after spring break, we'll get serious and show you some 3x3s. Okay, so but let's just do this. Let's find. Oh, by the way, I need to say one more thing here. Can we come back to this list here? Where I wrote null space of A minus lambda I am going to start denoting that E sub lambda. And the reason I'm doing that is that it is actually, we probably all remember, right? Null spaces are always
subspaces. So this is actually called an eigenspace. This is called an eigenspace for lambda. I'm just gonna squeeze that in right there. I'll try to write that down again next time we get together. The eigenspace for lambda is just this null space. So what I would like to do, and because it is a subspace, I'm going to find bases for the E spaces. These are the eigenspaces of, so let me give you a matrix here. It's just a little 2 by 2 matrix, 1 and -3, and then 1 and 5. Let's just tackle this one example real quick. Okay, so I'm really just asking I'm asking you to find the eigenvalues and eigenvectors for this one example today. It's just gonna do one example, and then we'll come back to this after spring break. I just want to get this started. The way you're gonna do this is you're first going to figure out what the eigenvalues are, what the lambdas are. Now, how do we do that? By using this characteristic equation here. How does this work, by the way? We take our matrix A and we're going to subtract lambdas off of the main diagonal. So the identity matrix, just remind everybody here, guys, the identity matrix is what? It's got ones down the diagonal like this, right? Zeros everywhere else. If you multiply that by lambda, you just turn all of those ones into lambdas. You have a bunch of lambdas on the main diagonal, and you're just going to subtract them off of A. And we're going to take the determinant of that. So here's the way it looks, guys. You literally put minus lambda on the diagonal entries of this matrix. So this matrix right here, just so it's clear, this is the matrix A minus lambda I. That is what that matrix is. And what the characteristic equation says is that we should set that equal to 0. So I'm going to set this one equal to 0. Now, it's only a 2 by 2 matrix, so we have a nice formula for that, right? AD minus BC, a little easy formula for this. So this is 1 minus lambda times 5 minus lambda, and then minus -3, which is the same as +3, equals to 0. And this just becomes a quadratic equation. Let me just FOIL that out. If I FOIL it out, I'll have a lambda squared here, minus 6 lambda. And then there's a +5 here, 1 times 5, but there's also a +3. Combining those together, it becomes +8. So this is a quadratic equation in this case. It is a second degree polynomial. That's because it's a 2 by 2. If this was a 3 by 3 matrix, then we would get a cubic equation right here. And when you have only a quadratic equation, you can always get the roots because you have a quadratic formula. If you need to use a quadratic formula, you can. However, I'm just going to do this one by factoring it because it does factor nicely. By the way, guys, don't get used to that. We're going to have lots of examples that do not factor nicely after spring break, unfortunately. But for right now, these factor very nicely. And my lambdas are 4 or 2. Those are my lambdas. Okay? And so I have 2 different eigenspaces. I have 2 different null spaces that I'm going to need to look at to find the V's, the eigenvectors. And so that's the second part of this then, is to do those null spaces. So let's just make 2 columns here, and I'm just going to write these out. The first one on the left side, I'm going to do lambda equals 4. It doesn't actually matter which one you do first or second or third or anything like that. So I'll just start with lambda equals 4 because I happen to have it in the beginning here. And I'm going to take the null space of what? Of A minus 4I. That means I'm going to take A and subtract 4 from the main diagonal entries.
So I take this matrix A and I subtract 4 from the main diagonal entries and it becomes -3, -3, and then 1 and 1. Now, when you look at that, it should be pretty obvious that this matrix is not invertible. 2 rows are actually multiples of each other. That has to happen because what was the determinant of this matrix? It was 0, right? If the determinant was 0, then it's not invertible. I'm not surprised to see this. I can cross off that row, which I can cross off either row. I'm gonna cross off the one that has the -3s in it and just make a little pivot next to the 1 here. And I've got my X and my Y like we have done many times. And I notice that the Y is free, so I'll call that T. And then X will become -T. Everybody see that? Because X plus Y is 0. X plus Y is 0, so these two things have to add up to 0 here. Finally, to get my basis, how do I get my basis now?
Bust out variable.
Bust out that variable, exactly. So this is the basis for E sub lambda equals 4. Just gonna write it like this. When I bust out that T, I just get the vector -1 and 1. -1 and 1. Can you guys see that okay? Sorry. Sorry about that. I got a little bit out of space down there. So that's the basis for the eigenspace E sub lambda equals 4. It's just the vector -1 and 1. Good enough? Okay. Now my other eigenvalue just gives me a chance to practice it one more time. Okay, so here I'm gonna do a null space again. But this time I'm gonna take the matrix A and I'm going to subtract 2 from the main diagonal, right? So my main diagonal is 1 and 5. I'm gonna subtract 2 from that and I get -1, -3, 1 and 3. And once again, that matrix is not invertible. It can't be. Actually, if you get this matrix written down and you realize that your matrix is invertible or that you do have pivots going all the way down, you better check your work. Either your lambda value is wrong or you set up your null space wrong, miscopied a number, who knows what it is, right? But this matrix cannot be invertible. I'm gonna cross off the row that I don't like as much, which has all the negative signs in it. Circle my pivot around that second row on that 1. And then again, I can set up my free variable. Y would be equal to T here. X would be equal to -3T this time. And so my basis here, my basis for the eigenspace corresponding to lambda equals 2 would be, can somebody tell me what am I gonna get when I bust out my variable here? A -3 and a 1. Yeah. Just in case you don't believe me, if I put -3 and 1 right here, and I multiply this out, I get -6 and 2. Lambda was 2 right there. I go from -3, 1, I multiply it, I stretch it by 2, and I get -6 and 2. I'm just a magician. I can figure out how to get scalar multiples of my vectors just very directly. Just that simple. You guys follow this? You know what the hardest thing is about this chapter? I hate to tell you this. The hardest thing about this is that when the matrix is larger, you have to factor this darn equation, right? So for a quadratic equation, it's not so bad, right? We can all use a quadratic formula or whatever. But then if the matrix is 3 by 3, it's already a cubic equation. And we don't have nice formulas for that. So that can be, in many cases, the hardest thing we have to do. There are some tricks to getting the eigenvalues right, though. There's ways to check your answer. Can I tell you this now? I'll tell you this again in 10 days. If you take your matrix A and you add up the main diagonal numbers, it turns out it is always the same as what you get when you add up your lambdas. Oh, it's a weird thing, but the trace of the matrix, which is the sum of the diagonals of the original matrix,
is actually what your lambdas add up to. Has to be.
And one other thing, if you take the determinant of your original matrix, 5 plus 3 is 8. It always has to be the product of your lambdas. It's pretty sweet. I'll write all that down after spring break. What I'm going to do, guys, about this homework is I'm gonna make a little video for you. It will be 5 minutes long to explain problem 9 and problem 16. Is that fair?
Sound good?
I'd like to do that. I will do it tonight and I'll send it all out to you guys. And then if my other class asks more questions, I'll do more questions. The video might get longer if that happens, but I'll help you with the homework through a video. I think that'll be fine. Have a great spring break, everybody. I hope you have a lot of fun. Take a break, get some rest, get some sleep. And I will see you on the other side, if not before.
You too, you too.
Thank you.
Going somewhere? You say you're going like out of state?
I am going.